series of bytecode operators, flow of control and operations, and like any language, if you knew what the bytecode stands for, you can read it. Okay, so there is actually a lot of similarity there, and the similarity extends to things that we worry about within the data engine. We worry about questions like, should our execution environment be RISC or CISC? How complex do we make the kernel, and hence how big do we make the kernel? Right now we're obviously CISC for data operations. It's hard to argue that a merge join is not a complex operation. But for a lot of other operations, we follow a very much RISC approach. So we're CISC for the things that we have to major in, and we're very much RISC for the things that we minor in. We also are very much concerned about issues like dynamic recompilation. Right now, the SQL compiler makes a guess based on statistics. What order should I do the joins in? Which do I do first? Which do I do second? How do I group it together? The consequences of a bad choice are characterized as bad. One of those bads where it shouldn't be in quotes, because if you're talking about double-digit terabyte transactional systems, a bad choice means query runs days, really days. A good choice could mean query runs seconds. And it's all based on information that we have about the distribution and demographics of the data. So if for some reason we think we're dealing with a 12-row table, and there's 60 bazillion rows in it, we might make the wrong choice. And you would hope that if we thought there were 12 rows in the table, by the time we hit, well, maybe not the 13th row, but maybe the millionth row, we'd go back and say, hang on a minute. Maybe we should go look at that one again, and on the fly recompile the remainder of the plan, so that I can get more intelligence reacting to the runtime characteristics of the system that I've observed at the time. We also ask ourselves silly questions like, given we've got all these swell Java operators already, why do we want to build our own comparison operators? Why do we want to build our own flow of control operators? What sense is there in doing that when there's a huge library of that already available? And then a host of other problems that in the interest of time I'm not going to go through, but how do we determine what to, okay, I'll go through them anyway. How do we determine what to keep in a buffer pool? How do we determine when to take a class that's no longer active and toss it out of the VM? Very similar kind of question. How do we keep the environment up and running for years at a time? We do have a framed letter in one of the conference rooms in the building that I work in. It's a letter from the president of Fuji Bank to the CEO of IBM, congratulating him on Fuji Bank's 2000th day of 100% uptime of one of our database products. So we do measure uptime for a lot of these things, not in hours, days, weeks, but in months, years. And we do have requirements for things like continuous availability, up to and including how do you replace the database on the fly without making the data unavailable. So changing the data engine without having it appear to the end user as though any of the data is unavailable.
Jim, 10 minutes.
10 minutes, right. How do we scale? Do we scale up to bigger SMPs, or do we scale out to clusters? So lots of questions that are very similar because the problems are very similar. So that's the server side. Obviously, a lot of similarity there, a lot more than we might have expected at first blush. What about the client side? So if I look at a typical business application that involves database, something like I want to display all the claims for a customer who's called into my call center. I want to be able to access a lot of different data, form, billing, history, claims history, things like that, so all their information's available when I go to look for it. I also want to be able to do things like sort and aggregate the results on any field of information on the fly. They could call in, I don't know what they're going to ask. So the ability to access any bit and reorder it so that I can access the bits quicker is an important requirement. And there could be a lot of it. A lot more in many cases than would conveniently fit on the client's desktop. From a database perspective, it means you connect to the database, you retrieve information from one or more tables, you populate the screen with data that you've retrieved, but there could be more coming, so you want to continue to asynchronously fetch the rest of the data after you've painted part of the screen, give control back to them. A lot of this data is interrelated, so being able to construct a graph of objects that are related, spilling them to the disk if they don't fit into memory. And a lot of people would scratch their heads and say, isn't that what virtual memory systems are for? And you could answer yes, but you really want to push your virtual memory system like that for something like this kind of data that you know you might not look for. This isn't active working set data. This is stuff you might decide to scroll for. You really want it as part of your virtual memory at that point. You could argue one way. I'd probably argue the other. Being able to sort on any attributes on the fly, being able to access any, to aggregate on the attributes. There's also a lot of transcoding involved in database operations, moving from one character set to another, because by definition in most client-server environments, the server is a centralized repository for a large number of clients that may exist in different locations. So they may want to access the data using different languages and different character sets. Very common. Okay, so what we see in this list is the beginnings of what looks like the same list we saw for the server. The ability to do many of those same basic operations, to be able to have this fundamental set of data types that go beyond what can simply be stored in memory. The operations to act on those data types. Another typical business application would be something like a stock exchange, where they've got a large number of buy-sell requests that they end up having to pair up in the presence of regulatory and business rules to determine what gets satisfied. So the ability to process lots of data, again, might be conveniently partitioned, might not be conveniently partitioned. Transactions, and again, the speed is important. You might think stock exchange is a limited application. How many of those are there? Okay, pretty small market. But in fact, the same kinds of requirements, pairing buyers with sellers, processing large amounts of data in that way applies to things like auctions. A lot of travel kinds of sites. I want to go out and search for an available site. You go to Orbit, somebody like that. They're applying much the same kind of data infrastructure as you would find at a stock exchange. Media for pub/sub kind of purposes. A data stream coming in, being compared against a list of people who have subscribed to news feeds of that kind. What do they do? General clearinghouse operations, in-store credit verification, basic retail, a lot fit the same basic profile. Okay, and what this adds to our previous list is my data operations have to have local speeds and feeds. If you go out to Expedia and you want to look up a flight, every time you look up the flight, it's not going to go back to the central database because that just ain't going to scale. It ain't going to go fast enough. It has to be able to do a lot of the lookups on local data, on cached data. And the same holds true for things like auctions. The ability to act on a substantial portion of that huge pile of data that's been transiently cached locally.